Welcome to my presentation, a brief introduction to organic compounds and their importance. Alkanes are organic molecules that consist of carbon and hydrogen atoms, which are connected by carbon-carbon or carbon-hydrogen single sigma bonds. This means that they are unreactive to most chemical reagents. They are saturated hydrocarbons, saturated because all the bonds are single bonds, and hydrocarbons because the only atoms present are carbon and hydrogen. This is also known as a homologous series. As seen here, butane is an alkane with a chain of 4 carbons. As you can see, the length of the carbon chain directly impacts its state of matter, i.e. butane is a gas. The naming of organic compounds is governed by a set of rules to ensure a rational and systematic approach that allows any organic molecule to be easily identified. Firstly, you find and name the longest chain of carbons. Secondly, you identify and name groups attached to this chain according to the table seen on the page. Thirdly, you number the chain consecutively, starting at the end nearest a substituent group. Fourthly, you designate the location of each substituent group by an appropriate number and name. Lastly, you assemble the name, listing the groups in alphabetical order. It sounds complicated, but let's have a look. So we have our first molecule here. You can see that the longest chain is 6 carbons, so we know that this is a hexane. Secondly, we can see 2 groups. They are both methyl groups of 1 carbon. Next, we ascertain the shortest distance to the alkyl group. In this case, the groups are both attached to the 3rd and 4th carbon, regardless of which side we read from. Lastly, we add our information together. So we end up with 3,4-di, because there are 2 groups, methylhexane. Pause the video and have a go yourself. Good, did you get it? The second molecule is a pentane with 1 methyl group. Remember, it's 2-methylpentane, not 4-methylpentane. Number 3 is also pentane, but we can see 3 methyl groups. This makes it a trimethylpentane. Counting the atoms, we end up with 2,2,4 trimethylpentane. Alkenes are unsaturated hydrocarbons with a double carbon bond, consisting of 1 sigma and 1 pi bond. The double bond makes them stronger than alkanes, which means that their boiling points are higher. However, alkenes are also nonpolar and have weak van der Waals forces, resulting in lower boiling points in other functional groups. The 2 carbons in the double bond are both sp2 hybridized. In sp2 hybridization, a 2s orbital bonds with 2 of the 2p orbitals. This forms 3 hybridized sp2 orbitals of equal energy, leaving a single 2p orbital remaining. The energy of the sp2 orbital is greater than that of the 2s orbitals, but still less than the 2p orbital. The leftover 2p orbital remains at its original energy level. For carbon, each sp2 hybridized orbital contains a single unpaired electron. There is a half-filled 2p orbital, meaning that 4 bonds can be formed. An sp2 orbital has 2 lobes and is shaped like a deformed dumbbell, with one lobe much larger than the other. The geometry of an sp2 orbital is trigonal planar, with the major lobes of the 3 sp2 orbitals pointing towards the corner of a triangle. An angle of 120 degrees between each of the lobes is seen. The remaining 2p orbital is a symmetrical dumbbell. In alkenes, each sp2 hybridized carbon forms 3 sigma bonds, using 3 sp2 hybridized orbitals. The remaining 2p orbital overlaps sideways with a neighboring 2p orbital, forming a pi bond. The pi bond is weaker than a sigma bond, but it is strong enough to prevent rotation of the carbon double bond. This means that alkenes are planar, with each carbon being trigonal planar. Alkenes are nucleophilic and commonly react with electrophiles in a reaction known as electrophilic addition reaction. This is where the pi bond of the double bond has been used to form a bond with an incoming electrophile and is no longer present in the product. Furthermore, a new substituent has been added to each of the carbon atoms. Alkenes react with hydrogen halides to produce alkyl halides. The hydrogen molecule is split and the hydrogen atom adds to one end of the double bond, whilst the halogen adds to the other. One example of this is the addition of hydrogen bromide. Hydrogen bromide is polar, so the bromine atom has a partial negative and the hydrogen atom a partial positive charge. The hydrogen atom acts as an electrophile and accepts a pair of electrons from the carbon bond in the alkene. The hydrogen-bromine bond breaks heterolytically, forming a negative bromine ion. This results in the formation of a highly reactive carbocation intermediate, which reacts with a nucleophilic bromine cation. Another example of electrophilic addition is that of a halogen. This produces a provincial dihalide. Bromine is a nonpolar molecule. However, when placed close to an area of high electron density, it can become polarized. In an addition reaction, the closest bromine atom acts as an electrophile, then the same mechanism as just outlined is followed. An alcohol is an organic compound with a hydroxyl group attached to a carbon atom. Alcohols can be primary, secondary, or tertiary. A primary alcohol has a carbon attached to one other carbon. A secondary alcohol has a carbon attached to two other carbons, and a tertiary alcohol has a carbon attached to three other carbons, as can be seen here. Alcohols have higher boiling points than comparable alkanes because of their polarity and their ability to form hydrogen bonds. Alkanes are nonpolar and are thus associated only through relatively weak dispersion forces. As the molecular size of alcohol increases, so does its intermolecular forces. Alcohols can be subject to reactions to form other functional groups. Primary and secondary alcohols oxidize readily, and today we will be looking at the full and partial oxidation of alcohols. Tertiary alcohols are not easily oxidized because there is no hydrogen to be removed by oxygen. The partial oxidation of a primary alcohol forms an aldehyde. This is done by a process known as distillation, as seen here. An excess of alcohol is used so that the aldehyde product is not further oxidized into a carboxylic acid. Removing the aldehyde as soon as it is formed also helps prevent this. The full oxidation of a primary alcohol yields a carboxylic acid. This is done under reflux, as can be seen, to ensure the full oxidation. The oxidation of a secondary alcohol gives a ketone. No special measures need to be taken to prevent further oxidation because a ketone cannot be further reacted. Aldehydes and ketones are both organic compounds that incorporate a carbonyl functional group of C double bond O. As just mentioned, they can both be synthesized by the oxidation of alcohols. Of this carbonyl group, there are two main functional groups that can be derived due to the fact that the remaining carbon has two leftover bonds. If at least one of these substituents is hydrogen, then the compound is an aldehyde. If neither are hydrogen and are an aryl or alkyl substituent, then the functional group is a ketone. Compared to alkanes of similar molecular weights, carbonyl compounds have higher boiling points than non-polar hydrocarbons. This is because of the polarity of the carbonyl group, caused by a greater electronegativity between carbon and oxygen. This charge separation causes dipole-dipole interactions significant enough to affect boiling points. However, because of the absence of hydrogen bonding, carbonyl compounds have lower boiling points than alcohols and carboxylic acids. Low molecular weight carbonyl compounds, such as formaldehyde, are soluble in water because the oxygen from the carbonyl group can engage with hydrogen bonding from water molecules. The hydrophobic character of attached alkyl chains starts to outweigh the polarity of the carbonyl group as molecular mass increases, meaning that higher weight carbonyl compounds are insoluble in water. Carboxylic acids are a functional group that contain a carboxyl group, or C double bond O and a hydroxyl group, on the first carbon. They are highly pungent compounds. Compared to alcohol, whose boiling points are already increased by van der Waals forces and hydrogen bonding, carboxylic acids have higher boiling points still. This is because hydrogen bonding between two acids creates a dimer, doubling the size of the molecule, which increases intermolecular forces. As we already know, increased intermolecular forces require more energy to break and thus have higher melting and boiling points. Carboxylic acids can also produce esters when heated with alcohol and an acid catalyst. This process is known as esterification. Esters are known for their pleasant sweet smell and are responsible for the aromas of many fruits. Ester names are derived from the parent alcohol and acid. For example, the ester name formed by ethanol and ethanoic acid is known as ethyl ethanoate. Ethanol is reduced to ethyl, whilst ethanoic acid is reduced to ethanoate. Esters are more polar than ethers, although less so than alcohols. However, they have no hydrogen atom bonded with an oxygen atom, meaning that they are unable to participate in intermolecular hydrogen bonding. This means that they have considerably lower boiling points than similarly weighted carboxylic acids. Amines are a functional group derived from ammonia that contain a single nitrogen atom with a single lone pair of electrons and 3 substituents linked by sigma bonds that can act as bases. Amines can be primary, secondary, or tertiary. Primary amines have one hydrogen replaced with an alkyl group, secondary amines have 2 hydrogens replaced, and tertiary amines have all 3 hydrogens replaced. It is, however, possible to have a quaternary amine, which is known as a quaternary ammonium cation, and is a permanently positively charged polyatomic ion formed by the alkylation of a tertiary amine with a halocarbon. Primary and secondary amines are polar molecules that are able to participate in hydrogen bonding, meaning that they have higher boiling points than that of comparable alkanes. Tertiary amines are also polar molecules, but they are unable to form intermolecular hydrogen bonds and thus have lower boiling points than primary or secondary amines. They do, however, still have higher boiling points than comparable alkanes. Primary, secondary, and tertiary amines have the ability to form hydrogen bonds with protic solvents. Therefore, amines have similar water solubilities to alcohols. An amide is an organic functional group that is derived from the bonding of a carboxylic acid with a primary or secondary amine or ammonia. There are 3 types of amide: primary, secondary, and tertiary. To name a primary amide, the suffix oic acid is dropped from the carboxylic acid and replaced by amide. An uppercase N is added to a secondary amide to indicate that a nitrogen is attached to an alcohol group. A tertiary amide follows the same pattern of nomenclature. Aside from methanamide, amides are solid at room temperature. The melting points for amides are high relative to their molecular size because they are able to form hydrogen bonds. In the NH2 group, the hydrogen atoms are positive enough to bond with a lone pair of another molecule's oxygen. These bonds require a lot of energy to break, hence the high melting points. Isomerism is where more than one compound with the same number of atoms, and thus the same molecular formula, have different physical and chemical properties. There are 2 main types of isomerism. One of these is structural isomerism. This is where 2 compounds have the same molecular formula but have a different structure. Structural isomerism can be further divided into 3 categories: positional, chain, and functional group isomerism. As you can see here, 1 bromopropane and 2 bromopropane have the same chemical formula C3H7Br, but they are different compounds because of the location of the R group. In this case, 1 bromopropane is a bromoalkane with the bromine on the first carbon, and 2 bromopropane has a bromine group attached to its second carbon. This is an example of positional structural isomerism. Another type of structural isomerism is chain isomerism. Chain isomerism is where molecules with the same molecular formula have different structures on the carbon skeleton. For example, butane and isobutane with the chemical formula C4H10 are different because of the methyl group attached to a second carbon. It may also be known as 2-methylpropane as per IUPAC nomenclature rules. Functional group isomerism is where the different arrangement of atoms in space yields different functional groups. For example, the movement of the oxygen atom from the hydroxyl group in ethanol to in between the 2 carbons on the primary chain results in methoxymethane, This gives a difference in functional groups, i.e. from an alcohol to an ether. In addition to structural isomerism, the other major types of isomers is stereoisomers. Stereoisomerism is where the connectivity of atoms in space is the same, but the arrangement of molecule in 3D space is different. There are two classifications of stereoisomers, geometrical and optical. Stereoisomers differ from structural isomers whose atom connectivity may change. Geometric isomers, also known as cis-trans or EZ isomers, occur when the order of an atom bonding is the same, but the arrangement is different. For example, in 2-butene, the double alkene bond is not able to rotate freely, thus leaving only two possibilities of arrangement, cis and trans. The cis isomer has two hydrogen atoms on the same side as the bond, whilst the trans isomer has the hydrogens on the opposite side of the bond. Geometric isomers need a rigid structure, such as a double bond, to form. Geometric isomers' physical and chemical properties can vary greatly, including their density and boiling points. The other category of stereoisomers is optical isomers. Optical isomers are known as enantiomers and diastereomers. Enantiomers are non-superimposable mirror images, or chiral compounds. An example of this is a pair of hands. Hands are identical mirror images, but if you try to move one on top of another, you'll find that they don't fit, or are non-superimposable. Try it now. Carbon molecules with 4 unique R groups are considered to be chiral compounds. Isomers are named using the LD, which is levo and dextro, or RS notation. Lactic acid, as you can see, is a well-known optical isomer. Non-superimposable, non-mirror image optical isomers are known as diastereomers. When enantiomers are a 50-50 mix, it is known as a racemic mixture. This is important in medicine because the human body can only metabolize levo-based amino acids. In pharmacology, some drugs are sold as a racemic mixture, while some are the levo enantiomer. Salbutamol, for example, is sold as a racemic mixture. The R, or levo isomer, is responsible for the bronchodilation, whilst bronchial reactivity is actually increased and the metabolism inhibited by the S, or dextro isomer. However, because the L isomer has 150 times greater binding affinity to beta-2 receptor than the D isomer, bronchial reactivity is mitigated and bronchodilation is generally achieved. Different functional groups can be identified using a variety of tests. The qualitative analysis of alcohols, aldehydes, and ketones identifies whether an unknown compound is a primary, secondary, or tertiary alcohol, or an aldehyde or ketone. This is because different functional groups react in different ways to different reagents. The process, reagents, and results can be seen in the diagram. Other functional groups can also be tested for. Alkenes, for example, can be identified by the unknown compound turning instantly colourless upon the addition of 1% bromine solution. Carboxylic acids become effervescent when solid sodium carbonate is added, and amines and ammonia yield a blue-green precipitate when 10% copper sulfate solution is added. All known organisms are carbon-based because carbon is able to form large macromolecules that act as the building blocks of life. Carbon is able to form 4 covalent bonds, and these large macromolecules act as a good skeleton for other atoms and molecules to bond to. 3 other essential elements, hydrogen, nitrogen, and oxygen, exhibit acid-base effects, which allows them to bond to carbon's foundational skeleton to form lipids, amino acids, and nucleobases. One example of an important biological organic compound is lipids. A lipid is a macrobiomolecule that is nonpolar, and thus hydrophobic and soluble in nonpolar solvents. It is worth noting that some lipids are amphiphilic, that is to say that they are both hydrophilic and lipophilic. This allows amphiphilic lipids to form structures, such as vesicles and membranes, in an aqueous environment. Lipids have many functions, including providing structure to cell membranes, energy storage, and cell signaling, which is directing which protein receptor a lipid needs to bind to in order to perform its functions. There are 8 main categories of lipids. One example is sterol lipids. A sterol is an organic compound with the formula C17H28O. Sterols are steroids where one of the hydrogens is substituted with a hydroxyl group. One example of this is cholesterol. Steroids help control metabolism, the development of sexual characteristics, and the regulation of water homeostasis. Another example is glycerolipids. Glycerolipids are formed of mono, di, and tri-substituted glycerols. One example is the fatty acid triesters known as triglycerides. In these compounds, the 3 hydroxyl groups of glycerol are esterified, typically by different fatty acids. Whilst talking about lipids, it is worth mentioning the difference between saturated and unsaturated fatty acids. Fatty acids are long hydrocarbon chains with an acid group at the end of both chains. Saturated fatty acids contain single bonds. Unsaturated fatty acids have a double bond, which gives the appearance of a kink in the chain, and polyunsaturated fatty acids contain more than one double bond. Proteins, including enzymes, hemoglobin of the blood, and the contractile proteins of the muscle, have the most varied functions of any molecule in the body. They play vital roles in cell function. Amino acids are molecules that include 2 functional groups, an amine group and an acid group. This means amino acids can act either as a base or as an acid. There are 20 types of amino acids that appear in the genetic code, with up to 500 occurring naturally that constitute monomer units of peptides. Amino acids are identical with the exception of their R group. It is this difference that makes each amino acid chemically unique and identifiable. Amino acids are the individual building blocks of proteins, as each amino acid is joined to by the next by dehydration synthesis, with the amine end of one linked to the acid group of the next. The joining is known as a peptide bond. A unification of more than 50 amino acids is the technical classification for a protein. However, most proteins are macromolecules composed of anywhere between 100 to 10,000 amino acids. In the process of translation, the genetic code contained inside mRNA is deciphered to build a polypeptide chain out of specific sequences of amino acids, leading to proteins with a variety of functions. This concludes my presentation. As you can see, this has only been a brief overview of organic compounds. There are lots more exciting things to learn and explore. Thank you.